Hey folks, welcome to my channel number 10. So we have the problem on our screen. Determine whether the following function is differentiable at the indicated value. The function given to us is mod of x plus mod of x minus 1, and we'll have to examine the differentiability at 2 points x equals 0 and x equals 1, right? Now before going into differentiability, I think we've got a bit of work to do in this particular problem. And whenever we get such functions, right? So we see that this is a summation of two functions, and if I can call the function as say h of x, right? My h of x has two functions, f of x plus g of x, right? And what is my f and g? My f is mod of x, and my g is and my g of x is mod of x minus 1, right? So this is how we write this equation initially. And as we go through this problem, you will understand why am I doing it this way. Because in these problems, you will have to be a little careful because in the case of f of x, the function will undergo a transformation at 0. But in the case of g of x, it undergoes a transformation at x equals 1, right? So when you rewrite this equation as h of x, you might have to examine more than one interval, right? And we're going to see how to solve for that first. So what is my f of x mod x? And I don't think I will have to repeat this. It is pretty simple. So I can straight away call it as my f of x equals x for x greater than or equal to 0, and my for x lesser than 0, I have it as minus x, right? This is my f of x. Now I come to my g of x and I'll have to write it in a very similar fashion, right? So what is that? Let's write that as well. So my g of x equals x minus 1 for all x greater than or equal to 1, right? And it's equal to minus of x minus 1, which is 1 minus x for x lesser than 1, right? So I have two equations in front of me. I have a g of x and an f of x. A g of x is undergoing a transformation at 1. So let me highlight it with a color, say green. And my f of x is undergoing a transformation at 0. Let me highlight it with a color yellow, right? So now we have to establish the differentiability of h of x. And what is our h of x? Our h of x is f plus g, right? So when I combine my f and g, and I'm going to call this as h of x, which I will write it out here, right? What do I get? So my h of x, which is equal to f plus g, and let's define it for x greater than or equal to 0, right? So what happens, my f plus g for x greater than or equal to 0 takes a value x, right? But though I am greater than 0, I notice that for greater than or equal to 1, the function takes x minus 1, and for lesser than 1, the function g takes 1 minus x, right? So, which means I will have to break the positive domain into two parts. Part 1 is between 0 to 1, and part 2 is from 1 to infinity, right? So that is how I will have to rewrite this function. So what happens is my h of x will take a value x plus 1 minus x for x greater than or equal to 0, but lesser than or equal to, but lesser than 1, right? So I'm going to combine this and write it as and lesser than 1, right? Comma x lesser than 1, right? I hope you folks are with me. And remember, we are still in the positive domain. We have covered the region from 0 to 1, and we're going to move to x greater than or equal to 1. So for x greater than or equal to 1, my mod of x remains as x. I don't have to worry about it. But my g of x will take a value, this time is x minus 1, right? And what is the domain we are working on right now? We are working on the domain x greater than or equal to 1, right? So this is the next part of h of x. So this entire thing corresponds to the positive domain, right? Inclusive of 0, right? So we are breaking it into two parts. And the way to write the first part, x greater than or equal to 0, and at the same time, x lesser than 1, we can rewrite it like this, right? 0 lesser than or equal to x lesser than 1. And for x greater than or equal to 1, we have got x plus x minus 1, right? I hope you folks are with me. So I can further simplify this. My x plus 1 minus x becomes 1, and my x plus x minus 1 becomes 2x minus 1 here, right? So this is how I write this, and looks like we've covered only the positive domain, and we might have to add two more equations. So let's add that, right? So now let me examine h of x for x lesser than 0, right? So when x is lesser than 0, my f takes a value minus x, right? So let me write that first. And then what happens when x is lesser than 1, which also means my g of x for all negative values takes a value 1 minus x, right? Right? And x lesser than 0, right? Are we done? Let's review this once again. When I go x less than 0, my f of x takes a value minus x, but my g of x, I don't have to really worry because for all numbers in the negative domain, I have my g of x taking the value 1 minus x for x lesser than 1, right? As represented by the second portion of g of x, right? So I don't think we will have to worry about the fourth part. We are done for the negative domain of x as well. And when I rewrite this, I get minus 2x plus 1, right? Minus of 2x plus 1, right? This is how we write this equation. H of x equals 1 in the domain 0 lesser than or equal to x lesser than 1, 2x minus 1 for x greater than or equal to 1, right? And we have minus 2x plus 1 for x less than 0, right? So this step becomes very important when we work out these functions, right? Because this is a combination of two functions, and it's very important that uh, we rewrite the equation with the appropriate intervals for x, right? So I'm going to delete this because now that we have this particular equation, and I'm going to move into solving the problem for differentiability, right? So let's examine differentiability at x equals 0 first. So for the sake of simplicity, I'm going to call this function f of x because we use the notation f for all our functions. So now that we have written our function, I don't think we'll have to really worry about whether it is h or f. So we can call it f of x now, and I'm going to start off with our RHD, right? So my RHD is f dashed of x naught plus equals limit h tending to 0 f of x naught plus h minus f of x naught divided by h, right? So my x naught is 0, so I can comfortably go ahead and replace my x naught with 0. And what do I have? My limit h tending to 0, f of 0 plus h minus f of 0 divided by h, right? And we will have to examine what is my function at 0 plus h. And what do we mean by 0 plus h? My x takes a value which is greater than 0 by an infinitesimal h tending to 0, right? So which is that function we'll have to pick up? We'll have to pick up this function where x is greater than equal to 0 but lesser than 1, right? So let's pick up that function for the first part of the numerator. Let's highlight that. So I think I can straight away write it out here. And I have my f of 0 plus h is 1, which is a constant, right? So I don't have to really worry about substituting x here. And what is my f of 0? My f of 0 is also 1, right? Because I have, for x equals 0, I still have my f of x represented as 1, right? So my numerator becomes 1 minus 1, which is 1 minus 1 equals 0 divided by h, and I'm left with a 0 by h, which is a 0, right? Because your numerator is an exact 0, your denominator is not an exact 0, it is a value which is tending to 0. So do not worry about substituting h equal to 0 in this equation, because 0 divided by any number which is not equal to 0 is equal to 0, right? So h being very small, it is not exactly 0. So remember that, folks. And all that we get is 0, right? So let's jump quickly to our LHD. We know that my RHD is a finite 0. And my so I have my LHD written on screen. My LHD is f dashed of x naught minus limit h tending to 0 f of x naught minus h minus f of x naught divided by minus h, right? So my x naught can be replaced by h as 0, and let's do that. And like we calculated in our RHD, what is my f of x naught minus h? It is when x takes a value which is lesser than 0 by an infinitesimal h tending to 0. And which is that equation? My equation is this, right? Because this is where x becomes lesser than 0. So all that I need to do is I will have to replace my x by a 0 minus h. And what is my 0 minus h? Is nothing but a minus h, right? So I can comfortably write this as minus 2 into minus h plus 1. And what is my f of 0? My f of 0 is a constant which is 1, right? So let's pull out the right. So I have minus 2x plus 1 rewritten as minus 2 into minus h plus 1, and then my f of 0 is 1, which is when x equals 0, we have f of x equals 1. So that is what I have written. And then my denominator remains minus h, right? So I can comfortably cancel out my 1 and 1. And then I have my minus 2 into minus h, which is nothing but plus 2h, 2h divided by minus h. And then I'm left with 2h by minus h, which is nothing but minus 2, right? So my LHD is minus 2 and my RHD is 0. So though both are finite, I can comfortably say that the function is not differentiable at x equals 0, right? Because my LHD not equal to my RHD. Therefore, function is not differentiable at x equals 0. Now, we've been asked to examine the differentiability at 1 as well, right? So let's move to x equals 1. At x equals 1, this is what I have. My RHD is f dashed of x naught plus equals limit h tending to 0 f of x naught plus h minus f of x naught divided by h. So wherever I have my x naught, I can replace it by a 1, right? So this is what I have, f of 1 plus h minus f of 1 divided by h, right? So it means my f of 1 plus h means x takes a value which is greater than 1 by an infinitesimal h, right? So which is that equation I will have to apply? I will have to apply the equation when x is greater than or equal to 1, which is nothing but this, right? So wherever I have x, I will have to replace it by a 1 plus h. So let's do that for the first part of the numerator. And I have a 2 into 1 plus h minus 1. And then I'm left with what is my f of 1, right? And for f of 1 is when x equals 1, right? And we still have this equation represented by 2x minus 1, right? Which is what we represented just now. Let me change the color. So 2x minus 1, which is highlighted in green. And what is my 2x minus 1 for x equals 1? It is 2 minus 1, right? Which is 1. So I can still call it as 1. And I'm left with a h in the denominator. So I can further write this as, let me copy this and move to the next line, right? And what do I have? So I have my 2 into 1 plus h can be written as 2 plus 2h. And then I have my minus 1 in the numerator still, which becomes a minus 2. And I'm left with 2h by h, which is nothing but, right? So my RHD at x equals 1 is finite and is equal to a 2. Now let's go ahead and see what is our LHD, right? Which is my left-hand derivative. So there we have our LHD written. LHD equals f dashed of x naught minus, that equals to limit h tending to 0 f of x naught minus h minus f of x naught divided by minus h, right? And what is our x naught? My x naught is 1, right? So I do that substitution and Let's see what do we get. So we have f of 1 minus f of 1 divided by minus h, right? And what is my f of 1 minus h? It is when x takes a value lesser than 1 by an infinitesimal h tending to 0, right? So which is that value here? It will be this. Let me change it to green. So it is going to take the value which is a constant, which is 1, right? So this is my first part of the numerator. And then my f of 1 is going to take 2x minus 1, right? Which we calculated in our earlier problem. So what is that? That is also a 1. So I have a 1 minus 1 in the numerator, and I still have a h in the denominator with a negative sign. So I can call it minus h. So I have a 0 by minus h, which is nothing but 0 divided by minus h is nothing but 0. H is not exactly 0. So this final form what we have does not take the 0 by 0 form. It is an exact 0 divided by a value which is very close to 0. So please do not get confused here. And what happens to this is nothing but equal to 0, right? So I have my LHD equals 0, my RHD equals 2, and what do we have here? My RHD equals 2, my LHD equals 0. Both are not equal, and RHD not equal to LHD, and therefore function is not differentiable at x equals 1 as well. So that's how we examine the differentiability of the function. So the final answer to this question is the function is not differentiable at both x equals 1 and x equals 0, right? So I hope you found this content useful. Please do subscribe to my channel and support. Thank you.